Hello, everybody. Welcome to the OIMC Live Solve. Good to see so many of you guys here. And today we're going to be live solving some of the questions, which means that none of us have seen the questions before. It's literally just, oh, wait, we have a counter medicine. Cool. But yeah, we're going to be solving the questions live, checking out how we do, and make sure you guys can always send your ideas, answers, or anything in chat relay, and we'll be able to see your comments as we move along.
Right, yeah, it's going to be super fun. Chat relay messages are going to be showing up down here. You can suggest thoughts or solutions to the problems, but yes, we will be live solving them. Like Eddie said, we have not seen them before, and I'm going to regret some of my decisions I make here. But that's part of the fun. So let's introduce each other. I am joined by Eddie from the only state whose name sounds like a greeting, from Ohio. He has won his math count state in Ohio. Also qualified for nationals, qualified for the Amy 3 times, and likes learning new languages, which is something that makes him very different from me. Eddie?
Yes, and thankfully, because you mentioned the greetings, this is how you say Ohio in Japanese, which sounds like Ohio, which is where I'm from. So from that, Eric is also really cool as well. Eric is a USA JMO winner, also a 5 times Amy qualifier on top of that, even went to Math Counts Nationals as well, representing Washington. And in his free time, he likes to swim and do a lot of other cool things as well. So awesome person as well.
Yeah, I didn't actually get it represented because it was 2020 and got canceled, but close enough.
Unfortunate.
Unfortunate.
Alrighty, let's hop into it. Do you wanna take the first one?
Sure. The first one I take is going to be the easier one, so I will jump on the opportunity. So, during Plainer High School's trip to the famous OIMC Math Museum, Amy notices that there were 4 times more cubes than pyramids. Furthermore, Billy notices that in the museum there were 96 more cubes than pyramids. Given that Amy's and Billy's observations were correct, how many pyramids were there in the museum? Why would you be counting 96 different cubes? So what's happening here is I have a certain number of cubes and I have a certain number of pyramids, and we want to find the number of pyramids in the museum. So let's let x be the number of pyramids here. X equals number of pyramids. Forgive my terrible handwriting. So 4 times more cubes than pyramids, so the number of cubes is going to be 4 times that, which is 4x. That's the number of cubes. And we also know that there were 96 more cubes than pyramids. So the number of cubes minus the number of pyramids is equal to 96. 96 more. And so from here we can solve our equation. 3x equals 96. Divide by 3 on both sides. That leaves us with x equals 32. If I have not made a computation error. Eddie, does that look right to you?
Yep, that's exactly what I got. I was actually going straight off of, yeah, Edison solved it in chat. So these are the 2 equations he wrote out. He's using C for cubes, P for pyramids, and bam, you get 3 pyramids is equal to 30. 3 times the number of pyramids equals 96. So P equals 32. Bam. So that was pretty straightforward. Moving on to number 2, which is going to, actually not number 2. We just did number 2. Going to the second problem in our list. Oh, and yes, the answer is confirmed to be 32. So the second problem in our list is going to be number 3. Alan is memorizing lines for a school play. On day 1, he memorizes 1 line, and then he memorizes 1 more line than on the previous day, and so on and so forth. So 1 line on day 1, 2 lines on day 2, etc. And so what day will he have memorized all 300 of his lines? So basically, why are there so many pyramids are in Egypt? I don't know. Maybe other places have missed pyramids as well. But let's just list out what we know first. So we know on day 1, I think let's do a table this way. So I'm going to just do a day on this side, and then the number of lines on this side. And then on day 1, that's 1 line. On day 2, that's 2 lines. Day 3, etc. But total, if we have a running total, this is just going to be 1. This is 1 plus 2 on the second day, 1 plus 2 plus 3 on third day, etc. We're just adding all the integers from 1 to whatever the day is. So basically, yeah, Edison has it perfectly laid out. We're adding to some point. So 1 plus 2 plus 3, etc. plus some day, I'm going to call that day n, such that this is greater than or equal to 300. I don't know if this is going to multiply exactly to 300 or if it's going to go over, but at some point, we just want it to be greater than or equal to 300. So is there a way we can simplify this? Well, there happens to be a formula for adding up an arithmetic series. But obviously, we don't want to just, plop the formula on the table. Where does it come from? So thinking about, I think the one I like to see is like, it's something, actually don't know what the actual name is, but I do know, I learned from my students the other day that it actually comes from Gauss. So a visual I like to use is like, if you draw, for example, this sequence. So I'm just going to draw 1, 2, 3, 4, all these dots, right? And then I'm going to double it. So I'm going to make the same image, but on the other side. So just pretend that this drawing goes on forever. But for now, I'm going to flip it and mirror it. So that's the same, not really mirror it, but like, I'm like reflecting it across the line. And then I make the exact same copy here. So the amount of blue dots, oh wait, this is not very lined up properly. This is not lined up properly, is what I meant to say. Okay, so now that we have that, we're going to do 1 + 2 + 3 + 4 + 5 and so on dots on the right side. And if you notice, what I did is just, I doubled the amount of dots I have. But the way we calculate this amount of dots is very simple now. The amount of dots on this side is just however many rows I have, which is n, for example. If I was adding up to 5 in this case, 1 + 2 + 3 + 4 + 5, I'm adding up to 5. So there's 5 dots in that for every column. Now for every row, it's 5 + 1. So generally, if I have n dots, if I'm adding to n dots, this is going to make some n by 1 times n rectangle. So no matter how many I have, here I just went to 5. But if I went up to like 6, 7, a million, 10 million, right? It's just going to be some rectangle. But keep in mind that I added the sum twice. So this can be represented by by the formula that Gia just put in chat, which is n times n + 1 for the rectangle. But since that's 2 times the sum we want, we divide that by 2. So this expression right here is equal to n times n + 1 over 2. That's like our nice formula that we're going to use. So from there, let's hope the pink shows up over the lights. N times n + 1 over 2 has to be greater than 300. I'm going to multiply by 2 on both sides, which means that I'm going to move this up a little bit, which means that n times n + 1 is greater than or equal to 600. And now it's just kind of guess and check. So like, what are some numbers that I know that add up close to this? So n times n + 1 is obviously very close to like just squaring the number. And I know 25 squared, if you don't know the trick, is if you square anything that ends with a 5, the squared version is going to end in 25. And then you take one number greater than 2, which is 3. 2 times 3 is 6. So you get 625. So 25 squared is 625, which is really close to that. So I know that 25 times 26 is greater than 600, but I might check 24. So what's 24 times 25? I don't want to do 24 times 25. I'm going to do 12. Okay, hold up. I don't need this anymore. Instead of doing 24 times 25, I'm going to do 12 times 50. That's much easier. And then 12 times 50 is exactly 600. So it works out. We know that n is 24. If I put n equals 24 here, it perfectly works out. And bam, we know that from our, I think I deleted the graph, but it takes exactly day 24 for Alan to memorize all of his lines. And so bam, E is 24.
Right, yeah, if I remember correctly, that trick was first used by Gauss. The legend goes that he was sitting in the 2nd grade classroom with his teacher, who, like many teachers nowadays, gave the students boring work to kill the time, asked them to find the sum of all numbers from 1 to 100. Gauss finished in 5 minutes, came up to her and was like, bam, here's the answer, 50-50. That's the story.
Wait, Adam makes a good point in chat. So what he says, why can't we just put n times n + 1 equals over 2 equals 300 immediately? So that's a really good point. Basically, we're like, if you at this point know, okay, if you plug in 24, it happens to be exactly 300, perfect. Because sometimes what the problem might do is like, it's not exactly 300, it might go over. So like, there's no number, no integer that you plug in that gets you 300. So for example, like if I made the number like, I don't know, 20, then on day 5, 1 + 2 + 3 + 4 + 5, that gives me 15. But on day 6, I get to 21. So in a case like that, you would just say, as long as it passes 20, it's fine. But here it works out that you get exactly 300. So it's nice that this works out. And yeah, you can absolutely just put an equal sign.
Yeah, Yeah, so you have to watch out for the going over case as well. That trick with the squaring numbers that end in 5 actually saved my life because it was like some sort of speed math competition. I forgot what it was. They asked what was 75 squared. I buzzed in too early without realizing they asked for the squared, and then yeah. Anyway, question number 8. Wow, we jumped all the way to up to 8. The coefficients of x squared and x fourth of the polynomial ax plus b to the fifth are 2, 5, 6, 0, and 3, 2, 0. Find a plus b. All right, so we're going to talk about something called the binomial expansion here. Say I have a simpler expansion here. Let's say I have x plus 1. Maybe we don't even need the 1. We could do a plus b to the 5th power. Or we could just do ax plus b, actually. It doesn't really matter. I'm kind of indecisive. But we're going to try to expand this. And obviously, expanding this term by term is going to be a complete pain. So we have to be a little more clever about this. I can rewrite this as ax plus b times ax plus b times ax plus b times ax plus b. I am running out of space. Hang on. 1 sec. There we go. Times ax plus b. Okay, well, looks like I did nothing. But consider, if I were to expand out this term, this entire thing, I would get 32 individual terms, and I can combine some of them together. But each of these terms is going to be selected this way. I'm going to have a factor from my first group. So let's say ax, for example. I have a factor from my second group. Maybe it's ax again. Then a factor from the third group. Then a factor from the fourth group. A factor from the fifth group. Like this is an example factor that I could get. But my point is that we're choosing factors from each of these binomials, each of these groups, and from there we can construct a term. And once I've done that for every possible combination, I will have distributed this entire thing. I would have basically expanded the factorization. But we have a little shortcut, because if we consider all the coefficients of x to the 4th power, let's say, coefficient of x to the 4th power. Well, to make x to the 4th power, I'm going to need 4 factors of x. So I need somewhere in here, I'm going to need 4 terms of ax, and I need one term of b, just b. So we need to find how many ways I could do that. And that's just 5 ways. 5 ways because I could choose which of these binomials is going to give me the singular b. 5 polynomials means 5 options. 5 times ax to the 4th power times b. So that's that has a coefficient of 2,560. What about the other one? What about x squared? That means that I need 2 factors of ax and 3 factors of b. And in this case, the counting is slightly more tricky, but there are 10 ways that I can pick two ax's from 5 things. So 10 times ax squared times b. If you're wondering where I got 10 from, it's because my first number, there's first ax 5 to choose from. The next one, there's 4 to choose from, but I could pick like this one first and then this one, or this one first and that one, which means I have to divide by 2. Or 5 choose 2. Yeah, I'm trying to avoid like the choose notation here, but it helps. If you know that, like this symbol, that's exactly what we're doing. I don't really want to go over that, but anyway, so we take this. We know that my coefficient of x to the 4th power is 320 and 2560 over here. So we are left with a pretty simple system of equations. That's a cube there. My writing is very slanted. Yeah. What do we do now? I guess we could just solve this, I think. What would be the fastest way to do this? So let's simplify both of these. Two, 5, 6, okay. So both of these powers of 2, Eddie, they look like powers of 2, right? They're just, A and B are just going to be powers of 2.
Yeah,
so.
I think that works out.
Oh, okay, so if A is 2 and then B equals 4, then this works, right? I just literally guessed that. But we could solve this the normal way, actually. But A equals 2, B equals 4. Sorry, I screwed up.
Yeah, that does work.
But
Nice.
I guess that. But let's try to actually solve this. So what I would do, I'll say, well, A to the 4 times B equals 2 to the 8th. A squared times B cubed equals 2. Now, what am I doing? 64 is 2 to the 6th. A squared B cubed equals 2 to the, that's 2 to the 8th. Okay. I'm probably just gonna square this over here. That's 2 to the 16th. I square my second equation and then divide. So b to the 5th power equals 2 to the 10. B is equal to 4. Plug that back in. We get a equals 2. And that. And so they're asking us for a plus b. And our answer is 6. You can't see it because there's a ring light on my face, but I am sweating because it is hot up in here.
Yeah, I actually have a fan going. It's pretty hot here too. But
I
yeah,
should not have left my window open.
I do want to go over the intuition that Eric mentioned though, because it is a nice problem solving strategy. It's like, I feel like nowadays a lot of the solutions are literally like, you can guess a solution first off by just looking at it. And that's what Eric just did, which is completely valid. And so this is Pascal's triangle, by the way, for those unfamiliar. I'm not gonna, yeah, we should avoid the choose notation for now, but something interesting to consider if you want to search that up. But yeah, like just to reiterate, Eric's point was like, if you notice that the two systems of equations that we ended up with is the fact that, wait, what are the numbers? 30, this is 64.
64, yeah. And then the other was 256, yeah.
Yeah, these are both powers of 2. And so it's very reasonable to guess that because we're dealing with powers of 2 variables, that these are just going to be various powers of 2. And so here you can just guess it from there. But honestly, if you want to, for example, like substitute, say like, hey, I know A is a power of 2, then call that A is like 2 to the C. And then you can substitute, do like exponent rules and stuff, and it might make the calculations easier. But that's just general problem solving tips. Pretty cool stuff. Alrighty. So moving on to the next one. How far are we gonna jump? We're on to number 11. By the way, yes, the answer was indeed 6. Wait, hold up. I'm on the right problem. Yes. Okay, cool. So we're on number 11. Number 11, which says, oh no, why is it not popping up there? Okay, I always get the long ones. Given the values, which of the following statements are true? Given the values of a minus b and a plus b, someone can determine the value of a times b. Given the values of a plus b and ab, someone can determine the values of a minus b. Given the values of a minus b and ab, someone can determine the value of a plus b. Okay, so this is a very interesting problem. So right away, I can say that as long as I get one variable, I get the other variable, because that's what the equations are. It's like, for example, imagine if I, for the first condition, said a minus b, wait, let's do it this way. If a minus b equals 3 and a plus b is 5, I'm sure we're very familiar with system equations. Add the two together, you get 2a equals a equals 4, right? And so as long as we can solve one of the variables, we get the other one because we can just plug back. Well, wait a minute. In every single one of these, it's saying we have 2 variables and 2 equations, which means they should be solvable. Obviously, unless they're like the same equation, but like that's not the case here. They're not multiples of whatever. They're not multiples of the same equation. So as long as I have 2 of them, I can get one of the variables, which gives me the other variable, and thus gives me the last expression. And since all of the ones are formatted like that, it's E, which is 1, 2, 3. But another thing you can think about is the fact that these are asking for the relationships between a minus b, a plus b, and ab. So therefore, we're saying from the first example, it's pretty clear that if we know what a plus b is, and we know what a minus b is, then together we know what ab is. But using this, wouldn't it make sense that if I didn't have a plus b, so say that this was gone and I had these two should be able to connect to each other and make a plus b. So it's not something special that like, oh, only these two give me the third. No, as long as I have 2 variables and 2 equations, it's going to give me the last one. So that's another logic. There's nothing like stopping me from going, okay, I know a plus b and a minus b and I know ab, versus, oh, somehow I know ab and a minus b, but I can't get that. So no, as long as I prove the first one, the rest actually follows.
I think you got kind of trolled.
Wait, is it not?
It's kind of okay. I think
Hold
2
up,
is
did I? Uh-oh.
no, because I thought it was E at first. I just looked at the code. I think it's E. I'm like, I checked the answer. Like, wait, what? And then yeah, chat comes in to help us.
Wait, I haven't been reading chat. Let me go check what it says. Okay, so it says for 2, addition and multiplication are commutative, so we don't know which one's A and which one's B, so we can't find A minus B. Oh, okay, I see. That is very valid. Okay, so I guess the safest way is to just do examples of all of them. So for example, if I went like, okay, hold up. So if I took, for example, let's do A plus B equals, I don't know, what, 4?
Well, the spoiler, the answer says 2 works, which I actually don't feel like 2 is going to work because you can move A and B, reverse the order, and then you have the exact negative of what you're, so you.
Well, yeah, that's the thing. So like subtraction is different because A plus B doesn't matter like which one, like, so A times B is something, right? So let's just say, I don't know, 6. So if AB is 6, that's going to give me something times something is 6, but no matter what way I add them, it's always going to give me 4, right? If I add B plus A or A plus B. But the problem is subtraction is different. The point is A minus B is not the same as B minus A. Therefore, it matters which one A and B are, and you're not going to get that from just these 2 equations.
Wait,
But
so
yeah,
what
2 doesn't make sense.
I might.
Hold
The
on.
answer
All right, then let's
says
just keep
2
testing.
only?
A minus, wait, is 2 should not be right, no?
2 should not be wrong. Is this?
Okay, hold up. Oh, yo, question mark?
I feel like only 1 should work. OIMC team says only 1 works. I'm not sure if that's the actual OIMC team or someone who named themselves OIMC team. Could you explain why it's not E again? Yeah, sure. So basically what happens is, let's say, because what's going to happen when you get A plus B and AB? You're going to have 2 different values for A and B, right? But you don't know which corresponds to A and which corresponds to B because both A plus B and AB, like someone said, are commutative. So A plus B is the same as B plus A times B is the same as B times A. So you don't know which one's B and which one's A. So then therefore A minus B can take one of two different values. I think it might be an issue with the slides, but.
All right, but yeah, 1 makes sense because, you know, the reasoning I was using earlier was
one is true. 1 is true, and this is going to be so cool. So I'm gonna explain why a really cool fact about math history. So back in like the Babylonians, they were like the first major civilization to have actual math. What they would do, say they wanted to multiply 2 big numbers, let's say 136 and 247. Okay? They wouldn't write it this way. They have base 60, which is a nightmare to work with. What they would do is they would say, well, if I have 2 numbers, A and B, and I want to multiply them together, A, B, what they would do is they will say, well, I would take A plus B squared, subtract that, A minus B squared, divided by 4. This is actually what they would do. Well, you might be asking, well, why would they make a square? A square makes their life harder. But what they have, they would carve these out on stone because they didn't have paper, obviously. Like huge stone tablets, just tables upon tables of just square numbers, for example, would be the one that we use here. So they would find A plus B, pretty easy. Look it up in the table. What is huge number squared? What is other huge number squared? Subtract them, pretty easy task, and then divide by 4, which is really easy task. So they will actually have like these huge reference tablets of all sorts of stuff, not just square numbers. You got squares, you got prime numbers, Pythagorean triples. It's really, really cool how they did this. And they were working in base 60, not like base 10, like we were used to. So multiplication for them is kind of a nightmare, right? Like you think about times table, it's like 100, it's like 45 technically, 50, 55, 55 different values for us to memorize. For them, it would be too many for me to think about, like 1800. That's not something that they're willing to do. I wouldn't be either. But anyways, they didn't even have variables. They couldn't even express their formula this way. This was only something that they knew, like a procedure that they could do because they didn't have variables. They just knew how to do this and they knew that it worked. They didn't know why. But my point is, that they knew a plus b squared and they knew a minus b squared, so they were able to get ab here. So that is really cool. I'm on such a tangent, but that's how I knew immediately that one was right.
Yeah, that was pretty interesting. That's really nice. I didn't know any of that, so that was a nice history lesson for me.
Yeah, but
Alrighty. Yeah, sorry. Did you have something else?
Hopefully I don't get such a
Okay.
get trolled on the next question.
Yes, I think the next one's yours, so go ahead.
Let's oh no, it's geometry. Suppose for variables x, y, and r, a gray circle of radius r is drawn. As shown, 4 circles are drawn externally tangent to the gray circle, such that the white circles are congruent with radius x and the light gray circles are congruent with radius y. And I realized that my chroma key that puts the slides up here does not differentiate between white and light gray. For all values x, y not equal to r, the value of x minus r times y minus r can be expressed as which of the following? What?
In the meantime, while we
Okay.
think about that, here's gray circles. My circles are still gray.
Congratulations. Okay, well I see tangent circles, and the first step when one sees tangent circles is to connect tangent lines. So I'm gonna use a little simplified portion of this diagram, and we're just gonna take 3 circles. So we have this circle, bigger circle, and a large circle up here. And so I'm just gonna connect the centers to the points of tangency, and I have a right triangle. A right triangle. We know it's a right triangle by symmetry. It's pretty clearly right. 90 degrees because it's 4 equal portions. And so I have a side length of x plus r, a side length of y plus r, and a side length of x plus y. Let's see. Can we use Pythagorean theorem? I'm trying to work this out. What do they want us to find again?
X minus r times y minus r. I think you might be able to do some epic manipulation.
X minus r times y minus r. Okay, I'm trying to think how this is going to play out. So, you know what? Let's just YOLO it. X plus y squared equals y plus r squared plus x plus r squared. Cool. I'm just gonna expand stuff then. Plus 2xy plus y squared equals, I think this is gonna work. Y squared plus 2ry plus r squared plus x squared. Yeah, okay, it's gonna work. Plus r squared. Right. I can cancel out x squared and y squared from both sides. I'm going to be left with 2xy equals 2ry plus 2rx plus 2r squared. What are the answer? Okay, the answer choices are in terms of r squared, which is very nice. Cool. And so now I'm gonna subtract 2ry and 2rx from both sides. I'm gonna divide everything by 2 first, and then subtract. So xy minus rx minus ry equal to r squared. And here we get to use a little thing called Simon's favorite factoring trick. I have no idea who Simon is. I can only presume.
I like to think it's one of the chipmunks.
Oh, one of the chipmunks. Can you imagine like squirrels just doing that? No, if I remember correctly, it was one person on a problem solving message board from 22 years ago. For some reason, everyone names it that now. But essentially, what this trick says is, well, I want to factor these 3 terms and then have something at the end of it. This is a little bit like completing the square, if you guys know what that is. So I'm going to start with, well, x times y minus r minus yr equals r squared. Cool. So I have x times y minus r, and I need a something else times y minus r. Well, I already have a y here, so I can say x times y minus r minus, well, I can say r times y minus r equals 2r squared. So what's going to happen is, well, I'm going to add an r squared to both sides. That's going to allow me to factor this. I'm going to take a look at my first 2 terms, factor out this, and then use this to figure out what I need to add to the end of this. And so we're actually left with x minus r times y minus r equals 2r squared. Another way you can visualize the Simon's favorite factoring trick is a geometrical one. So if I have, say, a rectangle here, split into 4 parts. And I already have an xy, an xr, and a yr. Technically, there's a negative there, but we don't have to worry about that right now. So you have x here, y here, r here, denoting side lengths, like that. Well, if I want to complete the rectangle, the only thing I ever need to fill in is just r squared. That's the area of my last segment I could use to finish the rectangle here. So that's another way. Yeah. I first learned the trick when watching a video of the guy who founded AOPS talk about it, wearing a black hoodie and sunglasses, pretending to be an alter ego of himself named Simon. That was an interesting experience.
Simon? I thought it was Harvey. Oh wait, was that another thing?
What? Wait, I swear he himself was named Simon. That's why he called it Simon Factory trick. I don't know.
Okay, I don't know. Okay, I have no idea actually. Maybe we can go fact check each other later. But another thing is you can definitely do Simon's favorite factoring trick. But another thing is just generally when you keep in mind the final expression, it was asking for x minus r times y minus r, right? And so once you get to this equation and you have to look for this, another way you can go is like, oh wait, hold up, I just need to add r squared on both sides to get this expression, and you get 2r squared. So that's another way of doing it. Alrighty. Looks like I get geometry too. Okay, so moving on to, this is number 14. So I have a circle of radius 13, so let's go ahead and mark that. I'm gonna just pick this line. Oh no, I can't. Is that the center? No, closer. Okay, and I'm gonna draw that right there. That's 13. And then a chord of length 24. So that one's length 24. Instead of drawing the entire length, I'm just gonna mark the halfway point and note that this pink segment is 12. And then from there, what is the difference between the side lengths of the two squares? Okie doke. So we know that the reason why I drew half the side length is right away, 13 and 12 on a right triangle is very nice because the final angle is, sorry, the final side is 5 because this is a 5, 12, 13 triangle. And from here, we just do a lot of math to figure out what the remaining side lengths are. So I don't know if this is the most efficient way to do it, but right now I'm looking at the smaller square, and I notice if I draw a radius from the far corner of the square to the center, where do you know that's 13? And then I'm going to mark the side length of the square in red. So the red side length is the side length of the square because it's just in the middle now. And then the upper part right here is going to be half that. So that's x over 2. So right now, I'm going to just move this diagram aside for now. Looking at the triangle we just drew, what happened is that we had the radius as the hypotenuse, which is 13, then half the side length of the square as one of the shorter legs. And then from there, the portion of the longer leg was the side length of the square. And the remaining part was the 5, 12, 13 triangle that we just found. So we know that the side length is 5. And so bam, we can do Pythagorean theorem on this thing. And then since we have one variable and one equation, we should be able to solve it. So this might be messy though. I really hope it isn't. So x squared over x plus 5 squared should be equal to 13 squared. And this is just a lot of number crunching from here. So I'm pretty sure this is going to be x squared over 4 plus x squared plus 10x plus 25. That should be equal to 169. And then from there, I don't want to multiply through by 4, but since we don't like fractions, that's what we're going to have to do. I know 169 minus 25, which is 13 squared minus 12, sorry, 13 squared minus 5 squared should be 12 squared, which is 144, because that's what we get from the 5, 12, 13 triangle. And from here, I can just multiply by 4. So if I multiply through by 4, I'm going to get x squared plus 4x squared plus 40x is equal to 4 times that, which is 576. And then that means we're just solving 5x squared plus 40x minus 576 equals 0. This is not going to be fun. I really hope that the numbers are nice. And because I have faith in the problem makers, I'm going to assume that this factors nicely and I don't have to use a quadratic formula. So let's hope that we can divide the first factor into 5x times x. And now we have to divvy up 576 such that 5 times the some version and then added to whatever's here times x, that gives us 40. So I'm trying to guess what numbers would be close. What's 576? So 576 is 4 times
24 squared.
140. Oh yeah, I don't know why I didn't think of that. Okay, right. 124
Yeah.
squared, which is going to be 2 to the 6th times 3 squared, which means this should be, what if we do
I don't know if they have
16.
a difference. I don't know if they have a difference of 40 though, because you have to have a factor of 5 there. Because the way at least I factor it, I don't.
Wait.
I don't think it's gonna be pretty. I'm sorry. I generally don't think
You're
it's gonna
right.
be pretty.
Wait. Okay. What was the question asking for? Maybe. Okay. It says, what is the difference between the sine lengths of two squares?
There has
Okay.
to be a better way to do that.
Are you able to just directly find the difference somehow?
Well, it's like this little segment here is half of that. I don't know if you can even find that segment. I'm trying to.
Wait. Okay. You know what? Let's revisit. Let me go match up our drawing over here. And then, is there a way to directly find b minus a? Or sorry, just the longer minus the shorter. Okay, well, I'm looking at if I just draw the longer side length right here. Bam. So I need to find this minus that. And how would we go about doing that? That was the question. Okay, what if we find, I'm hoping that we find another expression for the longer side just like this. And then for the longer side, and then magically it works out. And maybe with that, I don't know. Is that a thing?
I'm just rambling at this point, but could you do something with the fact that these 4 vertices are on a cyclic quadrilateral? I don't know if that's.
Oh no, I'm not good enough at geometry for that. I'm gonna hope that that's not the case.
Well, you got similar triangles if you.
Wait, watch. Okay, you get the exact same equation if you do this on the other side. So we know that this is a radius, right? And if I mark the longer side in yellow, sorry, the side of the longer square in yellow, half of this, let's call this y. Y over 2 is right there. And that's, wait, that's y. That's the side length minus 5, right? So therefore, the second equation says, looking at this triangle that I have in yellow right here, the second triangle says, I have a side length 13, then a y over 2, then y minus 5. I think this works. Y over 2, then y minus 5. And then using that equation, we're told that y over 2 squared plus y minus 5 squared is equal to 13 squared. And then from there, if I copy paste the equation from what we did the shorter side in red, what's going to happen is, so if I copy paste this, these are our two equations, right? And then I don't think we need the drawing anymore. So these are our two equations. They're very, very similar, except now this says y minus 5, this is x plus 5. Do we subtract that question mark? So y squared minus
with
x, because we wanted y minus x somewhere. So this is going to be divided by 4. And then plus y squared. Y squared minus x squared. Sorry, I want to use what? Okay, so y squared minus x squared, and then the 25, the 5 squared cancels out. So this is minus 10x. Okay, wait, what's y plus x? Hold up. Is there a way to easily get y plus x from the diagram? One sec, I'm thinking out loud as well. But like, how would you get y plus x? Is y plus x the chord? No. Because I'm thinking you set a variable to, you set y minus x to a variable. So, because I'm pretty sure you can factor out y minus x from this. Oh, wait, never mind. Hold up. So you get y minus 10x minus 10y. And then you get a bunch of x plus y's and x minus y's. So this says, okay, wait, let me just set up all my operations so I don't have to keep switching back. Bear with me, but okay, I'm going to move this up there. So plus, minus, and then minus 10. Okay, this is very long.
No one knows.
Good question. I will I believe it's what? Never mind. I get it. I bet it's online. Okay, maybe somebody in the chat can help us out here. Okay, that actually works out. Makes sense.
Wait, Eddie, I don't know if you can like, because I'm trying to find a way like we use diameter to our benefit with the fact that the right, but like Vienna jumping is something different.
Wait, okay, what if we set variables y equals y plus x and y minus x? Because therefore, if we set like, I don't know, a is equal to y plus x, and then b is equal to y minus x,
Does the y
what
plus
we
x
have is
term
a
cancel?
b over 4 plus, so that's just 5ab over 4, minus 10b. Sorry, 10a. And this is equal to 0. That's what we're told. Okay, so knowing that a times 5 over 4b minus 10 is equal to 0. Therefore, either a equals 0. Okay, we did it. Okay, so either a equals 0, because whenever two things multiply together to 0, either a equals 0 or 5 over, or this has to be 0. Clearly, a, which is y plus x, is not 0. Otherwise, both of the circles wouldn't exist. Therefore, 5/4 b minus 10 equals 0. Oh wait, I do not remember there being fractions in the answer. Wait, never mind. This is not a fraction. I messed up. Hold up. Okay, and then b equals 8. Is that an answer? Okay,
It
hold
is.
up.
It
It
is.
is. Oh my god. Wait, and it's actually b too. It's the answer choice b. All right. Moment of truth. Did I get it right?
You did. You did.
That was
I did
such
not.
a. Yeah, I did not expect that. I was like, how do we figure out a? But then it just works out where we have just a times something equals 0.
I'm
So
gonna be
that's
honest.
just a lesson. Yeah, do stuff until it magically works out.
Yeah, I'm gonna be real with you. I did not expect that to work. I saw a quote started doing math. Where step 1, do something smart. If you can't think of something smart, go to step 2, do something stupid. That is my life motto.
Yes. I'm gonna recap real quick. Sorry, wait, do you have something else?
No, go for it. Go for it.
Okay, I just want to recap what we did. Basically, as long as you get these two equations, that's what it mainly is. And from there, once you subtract, we know that this is equal to 0. And then the trick is substituting a equals that and b equals that, the difference. And then from there, I'm sure you guys know how to factor difference of squares, factoring that out. And then once you get to that, you factor out the a, and it's from there. Not that.
I guess.
Yeah, pretty cool.
I guess like the more important thing is you could just factor the y plus x from your equation without. I mean, the substitution of variables makes it a bit more clear, I guess. Yeah, which is probably more important. But
yeah,
after that one, I'm a little bit scared.
Yeah.
Okay. A, B, C, D, and E want to sit at a circular table together, but A does not want to sit next to E, D does not want to sit next to B. Under these conditions, how do you wait for them to sit at the circular table? What a creative question. Two configurations that can be the same, but rotating the table only count as one. Okay, it's one of these. So, okay, we have two conditions here. So, what could happen? Right, I feel like it's not going to be hard enough to just try and list all of them out. Though I am worried about like missing cases. How do I want to approach this? So let's we could use pi. We could use pi. We could do that. I think that's going to work. Okay, what we're going to do is we're going to basically count the total number of ways, then count the number of ways that don't work when the two people who don't like each other have to sit next to each other, the number of ways where that happens. The little complication here is that there's two conditions, but we can fix that by using a little trick called principle of inclusion and exclusion, which I will show in a bit. So let's start with the total. So there's 5 seats. And there's 5 people in the 5 seats. And what I like to do when I have a question where like rotating doesn't matter is say, okay, Adam, you sit here, and you don't get to question me. You sit right there. So Adam is always gonna sit. His name is Adam, right? Adam, good. Always gonna sit in the top seat, and everyone can just sit around him. That completely removes the restriction that rotating the table doesn't change it, because you're never gonna rotate something when Adam is always in the top seat. So therefore, our total number of ways is just 4 I'm gonna say 4 factorial, 4 ways to arrange the other 4 people. So my total is 24. Cool. So let's say Elijah sits next to Adam for now, and we don't care about anything else. We don't really, care about whether Bob and Daniel. There we go. We don't care about B and D sit next to each other. I'm not even going to bother checking names. I'm just going to say letters. B and D sitting. We don't care about that. We only care that E and A are sitting next to each other. So E, he has 2 places he can sit. Everyone else has 12. As six ways they could seat themselves. I can't tell. Which means that because there's 2 different ways for E to sit here or here, and then out of the remaining 3 seats they can go in any way they want. That means that there are 12 ways. So A/E 12. Eddie, correct me if I screw up, but I think this is right.
Wait, is that your final answer?
No, it's not my answer. It's not my answer.
No. I'm working on a different solution right now, so I have not been paying attention to what you're doing. My bad.
Cool. I understand. I do that a lot too. But so that's A and E case. Well, what if B and D sit next to each other? And I don't care if E sits next to A in this case, because we're gonna take care of that. We're gonna take care of duplicates and anything later. But let's say B and D sit next to each other, so they could sit in this pair, or in this pair. And they could either be sitting like B and D could sit here, or it could be D and then B. So that's 6 ways they could sit, and the other 2 people can rearrange themselves in 2 ways as well. So that also brings us 12 ways. And I know that I'm right because it's the same here, and it really shouldn't matter which people there are that have this restriction. They should have the same value by symmetry. Anyways, well, what happens now? I subtract 12 and subtract 12. There's 0 ways. Well, what's happened? What's the matter? That's because we intentionally ignored the cases where AE sit next to each other and the BD also sit next to each other. We're intentionally ignoring that. So let's see what happens. The case where both restrictions are violated. Well, I count that once in the total. I subtract that once in A and E. I subtract that again in B and D. So 1 goes to 0, then goes to -1. -1. I'm holding up -1 on my fingers. So that means if I want to count it 0 times, which is kind of the goal, right? I don't want to count this, but I don't want to like subtract too much of it. So I need to count that back up again. So I need to subtract. My pen dropped. I need to subtract AE. I need to subtract BD, but then I need to add AE and BD. And then in how many ways does this happen? Well, again, E can sit in one of these 2 spots, right? So that's 2 times, well then BD can be here or here, and they can swap amongst themselves. So that's 2 times another 2, which is I have 8 ways for both restrictions to be violated. So again, to recap, it's 24 minus 12 minus 12 plus 8. And that's going to get us our final answer of 8. Which, drum roll please.
I'm getting 8 as well.
Correct. Nice.
Cool. So I did it. So Eric did pi, principle of inclusion exclusion, which was really cool. And then the way I did it completely differently, I thought of like unraveling the circle. So basically, if you unravel the circle, and like it's just a continuous change of a bunch of like 5 seats, then Adam's gonna pop up in the 6th seat, if that makes sense. It's basically like you just pretend that the chair is now aligned, right? And the reason why I can do this is because, again, we're not counting rotations because we fixed Adam in the 1st seat, so there's no duplicates. And then reflections also don't matter as well. So they never mentioned anything about reflections. So that's like another reason why this works. So we're assuming Adam sits in the 1st seat, and that's the 1st seat as well because it just loops back around. Basically, by writing it out this way, I'm saying that the 5th person sits next to both the 4th and the 1st person, right? So Elijah doesn't want to sit next to Adam. So Elijah can't go here or there. Elijah has to go right here. And so knowing that, Elijah has to go in one of these 2, but they're actually symmetrical. So basically what happens is I can just count one of these cases, and then while that happens, I just double it at the very end because they're the exact same case. They're just like reflections of one another, but reflections are still different. So once I put Elijah somewhere, the only time B or D will sit next to each other is if they're both here, which means in order to avoid them sitting next to each other, one of B or D must sit over here. So that's two ways to pick one or B or D to sit here. And then out of the remaining C and whoever's left, there's two ways to arrange those two. So I get 2 times 2 for just this arrangement. And I doubled for the case where Elijah's over there because it's the exact same case. So you get 2 times 2 times 2, which is 8. Cool. Alrighty. So you know what's actually really nice is we have 2 questions left. So I'm hoping that we can, in these last 10 minutes, we can get through them. Alrighty. Is it my turn next?
I think it is, yeah.
Okay,
Yeah.
we're on number 18. So quadruples of positive integers a, b, c, d so that GCD, a, c, c, d, GCD, a, b, c, d equals 2 and LCM, a, b, c, d equals 40. Okay, so right away, we know that the upper bound on all of these, a, b, c, d can be no more than 40, which is equal to 2 cubed times 5. And the thing is, since the greatest common, so we know that the largest possible factor of 2 is, sorry, the largest possible power of 2 is 3, okay? So largest 2 is 2 cubed. But the GCD ABCD equals 2 tells us that, yes, they all have to be even. Thank you, Gia. So they all have to be even, or in other words, they all have to have a factor of 2. Oh, wait, is there not a slide with that? Okay, that's fine. They all have to have one factor of 2, but they can't all have a factor of, like, say 2 squared. So right away, I know that what's the best way to organize this? I'm trying to think. So
You could do prime factorizations of each of the numbers and see what happens. I think that's because like GCD is like the smallest out of all of them, and then LCM is like the largest out of all of them, I think.
okay, sure. So wait,
I feel like
I'm gonna list it this way. So I'm just gonna list a bunch of quadruples, and then at the very end, calculate how many arrangements there are of every quadruple, and then multiply. So like, we know we can't have, hold up. So okay, now that we've taken care of the factors 2, we know that the largest possible 2 is 2 cubed. And from that the lowest, there has to be some number in here that has exactly a power of 2 to the first. Doesn't have to be just 1, but has to be 2 to the first. Otherwise, it's not gonna work. We're gonna, if we have everybody's 2 squared, yeah.
All of them have to be divisible by 2, right?
Yeah. And then with the 5, we have to take care of the 5 as well. So the 5 means that, okay, the 5 means that at least one number has a power of 5 to the first, and at least one number has a power of 5 to the 0th. That's just how it works. And so it can't be such that all of them are 5 to the first or all of them 5 to the 0th. Can we multiply this? I'm trying to think.
Isn't like the multiplying trick only applicable to 2 numbers? That's what I remember.
Yeah, because what I'm thinking is like, because there's what, 24
table method
minus 2. Yeah, I guess we'll just make a table.
Your table method's gonna work, right? Yeah.
So do we do with powers of 2 and powers of 5 separately?
I think they're just completely distinct. You could treat them as 2 different worlds. That's
how do we merge them together, like the worlds together though?
Just multiply them, right? Because they're independent. Like, I feel like they are, right? I'm not going crazy, right?
Let me double check. So wait, there's 22 ways to arrange the powers of 5, yes? You either go 5 to the first, 5 to, okay, basically every number can either be 5 to the first or 5 to the 0th.
So there's 15 ways, and wait, no.
Wait, 2 to the 14.
14, thank you.
Sorry, I did 4 factorial instead of 2 to the 4th because I don't know what I'm doing. But yeah, so basically what we're saying is every number can either be 5 to the first or 5 to the 0th, right? But we can't have them all be 5 to the first. Otherwise, the GCD would have a factor 5 in it. And they can't all be 5 to the 0. Otherwise, the LCM wouldn't have a factor 5 in it. So therefore, the amount of ways to assign this is 2 times 2 times 2. But we have to subtract out the 2 cases that don't work. So there's 14 ways to do this. Are some of these divisible by 14?
B and C are only divisible. B and C are divisible by 14, which means that.
Okay, so there are numbers that are divisible. Okay, cool. So it's B or C. So those are the possible factors of 5. And then from there, okay, yeah, okay, I understand how I want to. Okay, makes sense. And now we're just looking for all the possible factors of 2. So there has to be at least a 2 cubed, and there has to be at least a 2 to the first. But we don't know. In the middle, there could be anything. So, do you just list them all out for this one? Like,
there's 9 options for your middle 2. Basically, that's not a 3 or a 1.
Yeah. Okay. Yeah. Right. So there's 9 options.
I think it's okay to list out.
Okay, so let's just. Wait. So I'm just gonna only list out the powers. So these are just 2 to the x, and I'm just listing out all the x table, like all the powers, right? So I could have the powers 1, 1, 1, 3, 1, 1, 2, 3, 1. Wait. 1, 2, 2, 3.
Way less than 9
1,
cases,
2, 3, 1, 2, 3, 3, 1, 3, 3, 3. Question mark? Okay, and then we just figure out how many ways there are to order this. Yes? Did I count this right? I think so.
I think you're missing a 1133 case.
Oh yes, I am.
Yeah.
Very yes.
Yeah.
Okay.
I think those are the only cases. I think.
Yeah, that makes sense.
6,
okay.
3 times 4 over 2. Yeah.
And so that goes right here. 1, 1, 3, 3. Right.
4.
And then so there's 4 ways to rearrange that. 6 ways. Sorry, no. 12 ways to rearrange that. 6 ways to rearrange that. 12 ways to rearrange. I'm basically just. I'm not sure if we have enough time to go over exactly why these calculations work.
We don't.
But okay. But yeah, we're basically just doing various permutations, combinations, all of these. Add these all up, you get 4 plus 12 plus that. Okay, I'm gonna add up all the 12s. So that's 36, and then that's 14. Oh wait, I should do this in different color. That's 14.
You get 50,
so you get
I think.
36 plus 14, which is 50. And so what we're saying is we listed out all the methods of these green combinations of powers of 2, right? And we said there's 50 of these. And then some combinations of powers of 5, and we said there's 14 of these. And then magically, every possible arrangement of these quadruples is just you connect these dots. In other words, we're just multiplying them. So basically, like for example, in the arrangement where we say like 1, 1, 1, 3, and then like 0, 1, 1, 1, the first number would be 2 to the first times 5 to the 0. And that's how you get all these ordered quadruples. So you multiply them all together, you get 50 times 14, which is an answer. Okay, 50 times 14 is 700.
Yes, let's go. And that looks
was fine.
That was fine.
That was a cool
We
question.
actually have one more question left, so
alrighty.
We'll try to get through this as fast as possible. Fred the Frog is at the bottom left of a 2x4 lattice grid of points shown here. Whenever Fred jumps over a point, he lands on the reflection of his position over the point. One day, Fred decides to jump 8 times, so all of the points in the grid are jumped over exactly once. After doing so, he finds the exact point he started on. Given this, find a number of different ways. Okay, guys, we're gonna end the live stream here. Thank you all for coming. I'm joking. I'm joking. We're gonna solve this, no matter how ridiculous. What? Okay.
Only 3 people solve this out of how many? OMC team, I'm curious. Out of how many people? Whoa.
I will say that this grid is a 3x5 grid and not a because the frog should be in the middle. Well, is it? No, 2x4 lattice grid. Oh, wait, okay. No, that is the right grid. Oh, okay, it's a grid, but there's spaces between. Wait, but there's
I thought a 2x4 lattice meant question mark 1, 2, 3, 4, like literally a 2x4
lattice grid, not just a grid. What is
it's this? No, it just do this. That's a 2x4 question mark.
What? Yeah. Wait, what?
Okay, diagram L. That's a diagram, certified diagram L. Okay.
Isn't this supposed to be the diagram? I know you can barely see the dots, but isn't that supposed to be? Oh, I don't see. Can you clarify it?
No, I think this is what lattice means. Question mark. Hold up.
Oh, AMC, could you, the frog is supposed to be in the middle of the square? Okay, that makes sense. That makes sense. So there's like points here, and the frog is on one of these points. Let's get rid of this false diagram.
Oh.
Okay, when you say jump across over a point, how is the frog ever going to get to the right side? What? Cause oh, the frog doesn't have to stay on the points. Oh, wait, okay. So like the frog could go from here to here and that would be jumped. Okay. So now that it's taken me 3 minutes to understand the problem, which is a great sign. Okay. I'm trying to think of how. So the main
This
restriction.
is crazy. So you can jump diagonally too, and this messes everything up.
Right, I want to say like we need to consider like how the ending jump is going to happen as well. Because that's the main restriction, right? Without that restriction, we can just go anywhere we want. The answer choices don't tell me anything about the problem either. It's a live solve. We didn't make the diagram. Yeah, we're not blaming you. We're blaming the. Two of the three people who solved them probably guessed because they both just guessed E at the end. Okay, I'm gonna try to solve this, even though we're technically past the hour limit. Eddie, you're free to help me as well because this is not gonna.
I am free to help you, but I don't know if I'm like capable of helping you on this one.
Okay, let's see. This is straight up borderline Olympiad level, okay? Your problems at problem 2 compared to problem 24. What is this difficulty curve? I have to say. But how am I ever? So it's gonna go over 8 points. Wait, that means he has to jump over his original point at some point in this process, right? 8 jumps. Yeah. Okay, we need a coordinate system for this, and then we probably have to express this with. So like if we let this be the origin 0, 0, and then we can have this be. Then we can. Because if I jump over, if I start from A, B, and then I jump over C, D, I'm gonna be left at 2C minus A, 2D minus B. Is that right? Wait. Because how does reflection work? Okay, so I have a distance of C minus A here, and C plus C minus. Yeah. So if I start from A, B, A comma B, and reflect over C comma D, I end up here. I feel like I'm not going about this in the right way because I want the number of waves, and how in the world am I?
Wait, honestly, can I preface this first off by saying our live solve time technically has it. We will no worries. We will spend the time and get this. But if you have to go, you guys are free to go. Again, thanks for
This isn't
today.
a class. They can just pop in whatever they want.
Yes, but
yeah.
yes, thank you for joining us today. Go scan. Wait, the QR codes are gone. LOL. That's funny. I think it's because wait.
I have the QR codes.
Nice, but yeah.
Suck it.
These are QR codes if you guys are interested.
Well, the other half are gonna get to see me struggle and
Alrighty.
suffer. Oh man. John 0512 solved it. He liked the math. He's a math god. What are you talking about? This is okay.
He competes in Ohio. That's all I got just for you. He was on my Arnold team.
I feel like. Oh, I have an idea for how we can approach this. Because with each reflection, you're never going to get like any closer to the center. Like if I reflect across this point, I land here. But then if I start from here, reflect across this point, I'm gonna land all the way back there. If I reflect across any point after that, I'm gonna land even farther. There's gonna be no way for me to recover. Basically, what happens is once I get outside of these two lines here, the +2 and the -2 lines. So once I get outside of that, I could come back. wait, I could start from, because if I come from back there and reflect, I could get on this line and get back. But if I go from any further, okay, so God. So one restriction, I can't go past, this is 1, this is 2. I can't go to 4 or greater, and I can't go to -2 or fewer. So I have a smaller grid here. Like I can't go past that line, and I can't go past that line. So this is 0, 1, that's 4, that's -2. That's a start, because you have to think about, otherwise you're never going to get back, and the thing is you have to get back to 0. Okay. I think the vertical bound, similar vertical bound, is not going to be very helpful here. Also, it's not -2, it should be -3, I think. -3. Wait, no, you still can get back with this, but oh, wait, okay. I think you have to consider horizontal distance as you travel, because you could technically get back, but it won't take enough. I have an idea for how we could start to bound this. So here's the premise. Say I only have 2 points, 1 and 2. We're not even going to consider the vertical axis right now. I might just reflect across one of these 2 points as many times as I like. So I could start from 0, go to 2, and I could go to -2. And so -2 reflect across 1. I could go to 4. 4 reflect across 0. I could go to -4. I could basically go farther and farther away from my lattice as I want. And when I want to go closer, I just pick the column closer to me. So like if I start from 3, right, I can either pick 1 to go to a closer point to 0, or I could pick 0 to go to a farther point from 0. But what I'm saying is your horizontal movement is limited to these 1-step increments. And there's 4 left column numbers and 4 right column numbers, which makes me want to think that, okay, so we're not going to consider the vertical axis right now. So I have 4 moves of 0, and 4 moves where I could use 1. And so we have to consider how I'm going to get back to 0 from this, a distance of 0. I think I'm onto something. So if we define like a function, a distance function, d here, and no, but 0s and 1s won't necessarily correspond to the increase and decrease amounts. Interesting. And like if I start at 0, I can reflect across 0.
Wait, are you doing distance from like the nearest like horizontal thing, or like from the
distance from
start?
the nearest horizontal point. Get me some support. I need some moral support here. Wait, OIMC, how long on average do you give a student to do this? I like to know. God. Because okay, if I count the number of ways that I could jump from left and right now, because I have a feeling left, right, and up, down are going to be separate problems. I have a hunch. It might not be true, but it's the only hope I got. Yeah.
What if we do it relative to like the origin? Like, wouldn't just go like 2.
I think what the origin is though, like, because if you're on the right side, you can reflect across point 1 to bring you closer. But if you're on the left side, you can reflect across point 0. Like it's not. You can look at the difference for like 0.5, for example. That might be a better. God, what is this problem? So you have 0 and 1. Does your chat say anything helpful? No, the Fred could go off the lattice. He just had to hop across each one of the lattice. Wonder if I've seen like problems where you like create mirror images of the lattice eye. Why did I say that? Which I must say that for these live solves, there's people selecting these problems for us to solve, which says someone solved this problem. I was like, yeah, I'm not able to. I think this would be a good thing for them to solve in front of people in a tight time limit.
I'll let Jesse know.
That's what I love most about this entire situation. Right and left. Okay, simpler situation. Let's say there's only like 2 hops, right? 2 hops. What's gonna happen? Okay, I have to go over 0 and 1. So I have to like use a 0 move and I have to use a 1 move. That's impossible actually to get back to the start with. I just realized. That's awkward. Sure, what about 4 moves? 0, 0, 1, 1. Well, I could go 1, 1, then 0, 0, right? Or I could go 1, 0. No. I feel like this is not gonna work. Cause here's what needs to happen, okay? I need to line up my moves with pluses and minuses, like plus the distance minus the distance. Like plus, minus, and maybe some nulls like zeros as well. Some of these have to correspond to increasing the distance away from the lattice. Some of these have to correspond to decreasing the distance from the lattice. The really challenging part about this problem is that they're not automatically correspond to each other. It depends on whether you're on the right side or the left side. It depends on whether you're 0 or 1. It depends on. So that's like what I'm really struggling with, because I need to get like this to a correspondence, because I could count plus, minus, minus. I know that plus has to be equal to the number of minus. I also have to land on 0, and I can't land on 1 at the very end. Maybe the answer choices can help me.
Eric, basically OMC team states that if you beg for their mercy, they will give you a hint.
I am not a coward.
Just kidding. They just said if you ask politely, they'll give you a hint.
Okay, so
wait, I have a message for OIMC team. Can I have hint, please? Pretty please.
5, 7, 6, 5. Like they're all multiples of 5, 7, 6, which someone in the chat also told me. 24. What special number does 24 squared have to play? 4 factorial. Okay, 4 factorial times 4 factorial. Very interesting. So 4 factorial has to come in here somewhere like this. Maybe I need to look at this like a little more big picture, but I feel like
Eric, I will say, check. Okay.
I am reading this. Yeah, Professor Lowe in the Discord.
Yes. Okay, let's read out the hint. So idea is you look at the x coordinates first. If you're on the point x, y, and jump over a, b, you go to 2a minus x, 2b
right, yeah,
minus
so
y.
that's what I wrote at the very beginning, like 2x, yeah, here.
Now we're just turning into a quarterback.
Maybe I should just go back to that instead of looking at weird reflection stuff. Well, if I just apply this a bunch of times, if I have points x1, y1, I'm intentionally not reading any of the hints and stuff, or like reading as little as possible. Like if I have a ton of these, well, first I'm going to start at x1, y1. I'm going to go to 2x2 minus x1, 2y2 minus x1. I'm going to have 2x3 minus 2x2 plus x1. Oh, so 2x4 minus 2x3 plus 2x2. Is this really all the problem is? Are you serious? Is that accurate? Is it just turns into a number pane? So yeah, you can do this to both the y and the x, and you have different values for Is that really all this is? Wow, I gotta say I'm a little disappointed. I think this is basically what's gonna happen is I'm just gonna apply the reflection formula as many times, like 8 times, which I was hesitant to do because I thought that would turn into a mess, but it's actually not gonna turn into a mess. I don't think the problem's gonna be trivial after this, but my throat is dying. Hang on.
I got you. We're sponsored by Dasani.
It's not even just honey. It's Kirkland. Right then. So we're gonna have 2 times. So there's gonna be 8 numbers I jump around. So I'm gonna start with x. So it's gonna be sum of -1 to the n equals 1 to 8, x n, because alternating positive and negative, plus, right, because I did a type, plus x0, which is my initial starting point, which is 0, so that doesn't really matter. That has to get me back to my original starting point. And then the same thing happens for the y values. Okay, I think, yeah. I just need to stop thinking about like the jumping and the distance stuff because that was getting me nowhere.
You know, this problem is so
So
hard to the point that the most interesting discussion in chat has been about water.
okay, I think we basically got it. Okay, x in the values it can take are 0, 0, 0, 0, 1, 1, 1, and 1. And so at this point, I just because the zeros don't really matter. So at this point, I need to have 2 positive ones and 2 negative ones among my 8 x ins. So I have 2 positive and 2 negative here. So that means that I have so I could arrange it's 8 choose 2 times 6 choose 2 for the x values. That seems to be Eddie. That's right? Because I want to put the ones. No, that's not right. Because
And I'm gonna be completely honest, I'm kind of lost.
okay, so out of the 4 even numbers, I can choose 2 of them, 2 ones. Out of the 4 odd numbers, I could choose. Oh no, but what? No, wait, no. Zeros don't matter. Yeah, zeros don't matter. I only need to care about the ones. They could go in positive or negative one. They're their only options. I have to do 2 ones in positive one, 2 ones in negative one. So it's actually just 4 choose 2 times 4 choose 2 for my x values. There's 36 ways. Please let this work. Y values. Y can take 0, 1, 2, 3, then another 0, 1, 2, 3. This is going to be a bit harder, but it still has to add up to 0, and I have to just throw them in the thing. So this total sum is 12, which means I have to have 6 positive and 6 negative. So I basically have to split 0, 0, 1, 1, 2, 2, 3, 3 into 2 groups of 6. And none of the groups, well, they have to be equal size, don't they? They have to be equal size, right? Because they're both 4 for each one. So there's only, you have 0, 1, 2, 3 and 0, 1, 2, 3, or I have to have 0, 0, 3, 3 and 1, 1, 2, 2. And those are my only options, right? Eddie, those are my only options, right? Yeah, because those are the only ways 4 numbers could add up to 6. Yeah. That those are my only options. So it's either this and this. Some of these go in positive, some of these go in the negative. So we're gonna tackle these 2 cases separately. So this here we have 4 factorial ways times 4 factorial ways. It doesn't matter which set goes in the positive, which set goes in the negative, because they are identical. So it's just 4 factorial times 4 factorial. In this case, we have 2 times 4 choose 2 times 4 choose 2, because there's 4 choose 2 ways to arrange each of the groups within positive, negative, and then there's one way to determine which group goes into positive, which groups goes into negative, hence the factor of 2, which means that for my y, I have 576 plus 72. And this is 36 up top for x. So we're left with 648 times. Am I doing this right? I have a sudden loss of confidence. Times 36. Which is not going to give me an answer choice, so we screwed up somewhere. Oops. Positive 1, negative 1, positive 1, negative 1. because exactly half of them are negative. And then I could. Which one has to be substituted in exactly? Oh no! Oh no! Because I could have duplicate coordinates if this happens. Oh no! Wait, I just realized. Okay, well that means I'm over. I'm trying to think. Because here's the issue. Because I could jumped over 0,3 and then jump over 0,3 again. In this case, how do you make sure that once I use 0,3, I've used 1,3? Oh no. So they're not independent. I can't just multiply them together. Wait, so it's not this simple. What in the world? This is gonna take the entire hour. I feel like I'm sitting in the USA JMO. You know what I mean? Like, I will say that I'm pretty sure this test has 25 questions, which means there's a question after this. Is that right? Or am I? So my alternating sum has to be 0. Well, I could. Okay, let's try this. What if I just add these two equations together? What happens then? Because in my coordinates, I have the sum of the coordinates. I have 0, 1, 1, 2, 2, 3, 3, and a 4. Wait, okay. They're having discussion in Discord. The professor though has solved this while I was talking, which makes me feel better.
He's joining.
God. What? Okay. While he's joining, I'm gonna keep going with whatever I think this is. God, xi. Because I could sum these up, but then I have to differentiate in between these, and then I'm not sure if that's gonna work, because that might be more cases than I can handle. I could probably just explain it. He likes watching me suffer. Okay, I should have just ended the live stream. I shouldn't have joked about it. I should have just ended the live stream. Okay, let's try, I don't even know what to say for commentary anymore.
I got you. So this is the type of question where, so the OMCT says that 25 is easier. So the lesson is, if this is that hard, you never know if the one after is going to be easier. Theoretically, yes, difficulty increases all the way through.
That's why when you do AMC, you always read the last 5 questions before attempting any of them. A little strategy for you guys who are still here. But I think I don't want to be spoiled on how to do this. Okay, let's try. I know I said let's try like 10 times without trying anything.
So basically, something.
Okay, well, 8 factorial is 40,320. I could try all 40,320 ways to see which one will work.
Valid. That's always valid. So 400,320, and the largest answer is like nowhere. Uh-oh.
If I try each combination, 1 second for combination, it'll only take me half a day. Anyways, okay, let's. Oh man. Okay, I don't think just straight summing is gonna get me anywhere because these two are gonna be linked, and I don't know.
I will say though that one pane geometry problem, that was fun. So that wasn't that bad at least.
That's nothing.
Let's talk about other math facts. Eric just brought up half a day. Half a day happens to be 43.
It's not exactly half a day.
Hey guys.
No, but it's
Our
the
Lord and
numbers really.
Savior has come.
Hey guys. I don't know if this will help. Let's see. So first of all, does my sound work? Hopefully this works. Hopefully
Yes,
everyone
it
can see.
sounds great.
Okay, sounds good. So by the way, no guarantees this will work, but this was inspired by watching you guys. Honestly, I didn't think of this myself. I just watched you guys. But it was something that you guys wrote early on. So I don't actually have something to write. So I'm gonna need you guys to help do writing. Let's see if I can do this. So here, let's see. I wonder if we can.
You spotlight both of us, maybe.
Should we join the Zoom?
You are on the Zoom. It's okay. I mean, you're on this one, so I think this will works well. Like, I'm just trying to think the best way to do this. If we do like some spotlighting thing where,
like a spotlight you.
You know what I mean? Like, if we can make sure one of you is able to draw, and then we can spotlight, or both of you draw, or something like that. You know what I mean? Let's do that. Let me switch it to gallery view. So then, in that case, everybody is going to see the four of us, just for a little bit. Okay. Let me just switch it to gallery view. Just a second.
All right, and we got some good Jeopardy music going. Anybody can play some good Jeopardy music. You know what? I should actually download that, and for like that way, in the future, we have that on hold.
Oh my god, for wood classes? Oh my god, that's actually so smart.
Okay. So now we're actually all on gallery view. So that means that everyone in the Zoom can see four of us. Everyone on YouTube can see four of us. So anything anyone else writes, we're all on the screen right now. Okay, so then the idea was inspired by what you said about if you think about where you are at, suppose you're at a point P, and then you jump over a point Q, then where you go to is you go to 2Q minus P. And so that's really important. The way you can think of that is like, where you start from and where you end up, they're going to add up to exactly double of the middle point. Does that make sense? That's what you guys said. Yeah. And now if you're watching this thing and you're not familiar with like, what am I doing multiplying coordinates, you should just think of the idea that if I had a coordinate pair like, I don't know, x comma y, and I multiply it by 2, it just becomes 2x, 2y. Okay, so that's the concept. And then like when you subtract coordinate pairs, you just subtract them in each position. So now the reason this is useful to think about in this way, by the way, this is called vectors. And that's why we have high school students who are hosting this. You learn about vectors at some point. Yes, and they're all capitals now, right? So these are vectors, right? And so when you add and subtract vectors, this is exactly what you do. Now, this is interesting because if you think about what happens after you jump over one more point, suppose you jumped over R, where would you go to? It's like P goes to 2Q minus P, and then that goes to 2R minus where you're at. So it's 2R minus parentheses of 2Q minus P.
Yeah, that's where I got this from. And then I just got stuck, and I don't know.
It's 2R minus the 2Q minus P, right? Because it's always like what you jumped over is that midpoint. Okay, and now the reason this is good is because now if you like open the bracket, it's basically 2R minus 2Q plus a P.
Yeah, sure.
But this is indeed what Eric was trying to do. And I just think this one, when you look at it this way, slowly, it might be easier for people to understand. So it's like if I jumped over two things, I just get to 2R minus 2Q plus P. I don't want to keep the parentheses. And the reason is because if you do it again, I guess what's next? QRS, right? If you do it jumping over an S and you think about what you get, is yeah, it's 2S minus, and then the signs flip. Right? And now you start to see a pattern coming along. Because if you are going to do this like 8 times, effectively what you're trying to do is you're saying I have the 8 vectors that 8 coordinates that I have. Those are what Eric was calling the 0, 0, the 0, 1, and whatever. But I don't want to give them names because that's too hard. I'm just like, I don't want to give them like, sorry, I don't want to give them those little coordinate names. I'm just the expression you're going to get is that you're going to be doing adding and subtracting of doubles of my 8 points in some order, And at the very end, it's a plus p, which makes me happy because you start with a p. And the surprising thing about this problem was, wow, how could you end up at the same place you started from? It turns out that that's automatic, that you get the plus p at the end. I was worried if it would be a minus p. But
yeah.
Is this making sense so far for like Eddie and Eric?
Yeah, it makes sense. I think that was like my idea at the beginning, but I split into like the different coordinates, and then I realized I couldn't do that because like if I jump over like 0, 3, and I could jump over 0, 3 again with my counting system. Yeah.
So it's going to be something like this of like the plus, the plus, minus. And then the deal is that you started from a plus p, which is, I guess, wherever you started from. And you ended up with this thing with a plus p. So you're trying to make all the 2 times stuff all cancel out to 0. So then the question becomes, okay, well, how many ways can I assign the 8 dots to those names, right? Like the thing that Eddie's drawn them, he's named them like from A to H. So he's like, okay, who's called A, who's called B, who's called C, all the way to who's called H. And the next thing I looked at was there's some symmetry here, which is that because it doesn't matter what order you add the pluses in, it's like if I chose the 4 things to be with the plus and the 4 things which should be minus, then there's 4 factorial ways I can mess around with the plus times 4 factorial ways I can mess around with the minus. So my answer is going to be, how many ways can I decide which are plus, decide which are minus, times 4 factorial squared?
Oh.
Does that make sense?
Oh, okay. So it's not even a system. You could just count them, list them out.
So then I started just counting how many ways can I on my nice diagram. You drew a nice diagram. You guys drew nice diagrams with like 4 dots, 4 dots. And I was like, let me count the number of pictures where I make half of them pluses and half of them minuses. And I have it canceled. Wait, first of all, is this making sense to people so far?
It makes, I can't believe, okay.
This is still non-trivial. Like I got to this point and then I was like, what do I do next? Because I need to then like start drawing diagrams with like 4 dots and 4 dots. And some of them I write pluses, some I write minuses.
Wonder if complex numbers could help us in this case.
So,
they're just...
I think here you don't need complex numbers. Here you need to exploit the fact that there are 2 columns. And that was inspired by something while you were doing your solution. I was like, oh, I see. So if you think about those 2 columns, it's like, well, how many pluses and how many minuses do I put in the first column? If you look at it, what you did is you split it to x coordinates and y coordinates. I want all of the coordinates to add up. I want all the plus points to add up and minus all the minus points and cancel everything out. And what you were doing is you were looking at it by the x coordinate and by the y coordinate. And if you start by looking at it from just the x coordinate, that's how you can see that you better have in your first column exactly 2 pluses and 2 minuses, and the second column 2 pluses and 2 minuses. And the reason you can see that is if you draw a case which is not that. Let's pretend putting all 4 pluses in the first column.
You have like too many ones
or 2 second column. You're going to get an imbalance on the x coordinate. Like if you just think about it from the x coordinates perspective, if you just imagine there's like 4 pluses on the first one and 4 minuses on the second one. Again, we should think of them as adding them as vectors or like adding them as points. Then you will get a problem because you're sort of like adding 4 times with the plus here, and you're subtracting 4 times with a minus, which is bigger. So you're not going to get 0.
Yeah, it's like, okay, yeah, I see what you mean by that. Like,
yeah.
Like going back to the coordinates thing, like even though I don't like to go back, I guess we shouldn't go back to coordinates thing. Like if the coordinates here is like 1, right? Then I want like all my sum of 1 to go back to 0. So it has to be 2 plus and 2 negative here.
Yes, and that significantly reduces the number of cases, because once you know that you need to have each of the columns be half plus, half minus, then I just started doing like brute force case of, well, let's start with the first column. What could I do? Plus, plus, minus, minus. And once you draw that, that's what Eddie has. There's only one way to balance that. That's the only way to balance that, because you're going to put 2 pluses and 2 minuses on the second column. And you need that the pluses y coordinates all add up to the same as the minuses y coordinates.
Oh, okay.
And you already gave the pluses big ones. It's like you, if you imagine the pluses y coordinates, it's like you gave the nice big ones over here. So the only way to balance that is to subtract across on the other side. Yeah,
Right,
at
so
least
like the sum of these two rows.
that's inspired by what you were doing there too. Yes. So those are the two so far, but there's, yeah, and then at that point, then what can you do next? There's the plus, minus, minus, plus, yes. And there's two ways to balance that.
Plus, minus, right?
Yes,
Yeah,
and as soon as I got there, I said, then I should just double everything. Because if I look at my left column, those three different left column possibilities, you've done all three different left column possibilities, the plus, plus, minus, minus, the plus, minus, plus, minus, and the plus, minus, minus, plus. You did all three of those. The other three will all be symmetries. It will be symmetric. If you just imagine doing, if you imagine doing the next one, you should be able to read off from a previous one. So I mean, if you actually just try to do it, oh, not that symmetry 6. I mean, like there's 8. What I mean is those 8 you've taken, or maybe I'm going too fast on this one. Let's just do the next one and you'll see what I mean. So the next one would be what? Minus, plus, minus, plus, plus, minus, I think is the next one.
Oh, there's one. Yeah, there's one more case. I missed that case.
Right. So now that one, you should be able to basically copy off what you did with the plus, minus, minus, plus, because you're effectively just changing the role of the plus and the minus.
Okay, we just flopped. Yeah. Okay. You flopped.
Okay, now you guys can finish that.
Okay.
You can finish the explanation because that's it.
8 times 4 factorial times 4 factorial, because there's 8 ways to arrange the. There's 8 ways to choose like which vectors go in the positive, which ways to go in the negative, and then within each of the positive, within each of the negative, there's 4 factorial ways to arrange each group. So 8 times 4 factorial times 4 factorial. You calculate that out. That's 4,608, and my torture has finally ended. So.
And that's it.
Wow, what a question.
Wait,
yeah,
I think so.
So actually, let me just flip it back. Let me flip it back to the speaker view. One moment.
Is it 4608?
It is 4608. Yeah.
Wow. Okay.
What?
I need to. I like kind of. I like. I don't. I need to think about this a little more. It's like
for how close I got to this solution. I like went and I didn't realize that the solution was like right under my eyes this entire time. I don't know. I just didn't realize that if you just combine the two and look at them with vectors instead of separate coordinates, you could make the problem so much simpler. Like
well,
that.
I wouldn't have been able to think of it if not for what you were doing. So I was just watching this. I was like, this is a really interesting question. And I was watching you guys come up with these ideas. And suddenly I was like, oh, maybe we can just systematize them. But it was really inspired by what you guys were doing. Okay.
Wait. Hold up.
I'm going to step aside now.
Okay.
You guys
Thank you so much.
You can take the rest of it. Yep. See you guys.
Bye-bye. Wait.
Wow.
Eric, can you explain this to me? Can you okay, so I'm struggling to contextualize what one of these solutions means. So like, if I put A, B, C, D here, and then E, F, G, H here, what does that mean? Like,
it's like
I should be going in the order A, like A, E, no, because it has to be alternate plus minus. So how, like,
well, like the order you do like A, B, C, D itself is accounted for like when we multiply 4 factorial at the very end. So you just have to consider which ones are we going to do on odd. Yeah.
But say I assign A, B, C, D here and then E, F, G, H there. Oh wait. Oh wait. Sorry. I'm stupid. My bad. Yeah. So that's going to be A, C, E, and then okay. Yeah, it's going to be A, C, E, G.
So it's going to be
and then that's the first one you do. First negative. Okay, I see.
OAMC, how much time did you give on average for Contestant to solve each problem?
Like, how much did you give for the whole test?
Yeah, how much did you give for the whole test? How much?
All right, well, I'm going to be thinking that's probably.
So literal AMC 10?
Oh, 25 questions.
Just 3 minutes. You basically have to know the entire layout of the solution. This is a really clever problem. Like, I actually generally haven't seen this before. I've never actually used the 2b minus a thing, which is why I didn't took so long for you realize that if you just applied it over and over again, you get something pretty cool. But well, guess we can end the stream there.
All right.
I'm gonna have to contemplate all my life choices now. They were like, oh hey Eric, you know the OMC live stuff is coming up, right? We desperately like live streaming with streamable people to like do this live stream. It was like in this spreadsheet, just like you just sign for the ones who read this was like, yeah, I'll sign it. OMC, that's probably like some weird middle schooler one. That's gonna be pretty easy. Nope. It's nope.
You know what's really funny is that I'm pretty sure there were 9 questions in this. Let me count. So 36 divided by 3 is
Yeah,
12.
there was 9 questions. So when I said that I got
no,
the easier
they're
was by
12. I
going
lied.
first, I was shooting myself in the foot.
And so the other 8 questions took us roughly like 50 minutes, let's say. And this question took us 45. So don't do number 24, guys.
The highest score is 145.5. I can see why.
Valid. You know what? That's a perfect score, you know?
That's basically a perfect score at that point. I mean, okay, here's the thing. Once you understand how the solution works, it's not a very hard problem. Like once you see how the solution works, it's not like bias of a hard problem. The issue is that like this problem is like so.
Thanks guys for coming. For those of you who sticked all the way to the end, thank you guys so much. We finally got all the questions done. So hopefully you found that pretty cool.
God,
I learned a lot. I learned a lot for sure. That was a very cool experience.
Yeah. Okay, I need to stop. I need to stop thinking about this. Otherwise, it's gonna ruin my life. Yes, thank you everyone for coming. That was most of the time that was fun. Thank you again to OIMC for making this competition, all these wonderful problems for us, with the exception of this one. And yeah, we have more live streams coming up. There's an Ask Math Anything on Tuesday as well, so you guys should come to that as well if you have any more specific questions that you personally want to ask us, for example. And we'll be doing more of these live streams all the time. So thank you, everyone. I know we went like 40 minutes over, but it was for a good cause. And yeah, I'm gonna go take a nap.
Well deserved nap. All right. Thanks, everybody. Good night.
Good night.